So who here either has been to a stargazing event or is looking forward to for the miracle to happen so that you go and see the stars this evening? With a show of hands, pretty much everyone. And I'm sure a lot of us here had those wow moments while gazing at the stars. You know, those moments where you feel something special. Not necessarily a psychedelic, you know, mind-bending epiphany, but just that feeling of awe, of you know, wonder under the night sky. Sometimes looking at the night sky triggers those feelings of, you know, big questions, deep questions that we ask as humans of where we come from. What is all this? What the hell is this? Why are we here? Why is this stuff around here? Why are there stars out there, and why anything exists at all? So what you see in the picture is a picture from a past event of astronauts. So these were people who came to these same facilities here to gaze at the stars. And I'm going to show you in the next slide a picture of another building where people used to go 5,000 years ago to do pretty much the same. So this is a monument called Stonehenge. It's in the UK. It dates to 2000 to 3000 BCE, and the orientation of this monument has an astronomical significance. Okay. This is another stone circle, very similar to Stonehenge. It's located near where I come from. It's in the north of Morocco. Who knows where Morocco is? Yeah, it's I think most of you do. It's in North Africa, the northwest side of Africa. So this is the north of North Morocco. It's a city called Larache in Arabic. And if you see, there's a picture on the bottom left. It's actually a stone circle. So the stones that you see and the other pictures are organized in the shape of a circle. And there is one particular stone which is much larger than the others. It's the one that I'm putting my hand on in the top right picture. The locals call it looted, which means pillar, because it's really very clear in the monument. And if you stand at the center of the circle, the sun will set exactly at that pillar at a specific time of the year. Not a lot is understood about this site. If you see the picture on the bottom left, it was actually taken by a let's call him an amateur archaeologist during the Spanish colonization of North Morocco, but unfortunately he disappeared during World War II, and he didn't publish his findings, so he pretty much disfigured the site, but he didn't publish the findings. So in Morocco we're waiting for the next generation of scientists to continue the works on this site to understand it a little bit more. If I had to list the list of monuments that have astronomical significance in the world, we will be past the 1 hour. It will be endless slides. It's tens or hundreds of monuments. The IAU, International Astronomical Union, publishes an encyclopedia in which they list these kind of monuments, and there are a lot of them. So here are just some illustrative examples. On the top left, it's a monument in China. The pillars are a reconstruction, but as you can see, it's a sort of calendar where if you sit at the right place, you will see that the sun sets at specific locations between the pillars according to the Chinese year. At the bottom left, there is a statue of an ancient pharaoh called Djoser from the third dynasty, and there is something which is very special about this statue over here, is that it was inclined specifically so that there's an alignment between the eyes of the statue of the pharaoh and the hole that you see here. There's actually two holes, and then if you continue with the alignment, they actually align to the north pole of the celestial sphere. So it's as if the pharaoh was allowed after his life to go through or to look at those specific stars that are around the north pole of the night sky, because it was believed back then that location of the night sky is a sort of portal to the afterworld. Why? Because the stars around the North Star, they don't set and they don't rise. They're always there. So it's pretty convenient and logical, it's intuitive to think of them as permanent and eternal, and maybe portals to the afterlife. Many other monuments. The picture on the top left are caves in southern France. It has been suggested that the dots that you see there, you see many dots. Thank you. The dots here, it has been suggested that they are the Pleiades, the 7 stars. And this is 17,000 BCE. Very, very, very old. So the fascination has always been there, okay? But the stories are different. So the stories that are told here in UCB when people do the stargazing events are very different from the stories that are told in these ancient monuments, right? So while on the left side in UCB, in other places in the modern world when we do science-oriented stargazing, we talk about James Webb Space Telescope, about spectroscopy, about all the satellites. On the right side, the stories are different. So they used to talk about animals that live in the sky, about the effect of the stars on our daily life here on Earth, and so on. But the fascination is the same. Okay, so that feeling of awe, it has always been there with us. There is a folk myth in Africa, actually in South Africa, that suggests the following question. What if the stars that we see in the sky are holes in a huge blanket that covers the Earth? Imagine this, actually. Imagine as if there were a very remote world that has very strong light, and then we are covered with a blanket or a cover that has holes in it, and the stars are actually those holes. What is fascinating about this question is that back then in the ancient times, there was really no way for anyone to tell whether this is true or not. So there will be a journey that mankind will follow to understand answers to questions like this one, and we will see how. So in the rest of this talk, we'll look at stops across this journey. The stops have been chosen by me, so this is not accurate history of science, but I've chosen some illustrative stops along the way through the journey through which mankind has discovered our place in the universe. So this is our first stop. It's the ancient Sumerian civilization. So this is contemporary to some of the monuments that you've seen earlier, but these are people who took it a step further. So instead of just awe and fascination with the sky, those are people who tried to, who pushed it a notch further, and they were more curious. They tried to understand really how the heavens work. They used a set of what I call superpowers. This is one of them. And this is the superpower of modeling the universe in your head. It's really amazing when you think about it. It's unique to humans as far as we know. It's the ability for us to close our eyes or not close our eyes and try to get out of our body, get out of this location wherever we are, and try to imagine how the world would look like from outside. So this is the earliest known map of the world. It was a very small world. So the circle that you see here, the small circles that you see here are actual cities in Sumeria. And these are the mountains that were surrounding the region. So this is a very local map of the world, but at least it's a tentative by someone long time ago to picture the whole world and to draw it or to carve it in these ancient tablets. This is the world according to ancient Sumerians. So it was a flat world, right? And there were layers of heavens above. There were initially 3 heavens, but also worlds underneath our world. There was a deity, Marduk. He was sitting in the 2nd heaven to look on everything. And down the road, in the Sumerian civilization, this became 7 heavens as well. So this is our starting point. Through the talk, we're gonna be unlocking some achievements. So humanity is gonna be unlocking some achievements, but this is our starting point, is that Earth is flat and the heavenly stuff are up there in the sky. The Sumerians did a lot of observation of the sky, what you see here is a very famous tablet called the Venus tablet, where ancient Sumerian astronomers documented meticulously, like day after day after day, the setting and rising times of Venus during 21 years. So this amazing body of works has been very important afterwards to help later astronomers to decode the heavens and understand phenomena that take thousands of years to happen in the night sky. So our next stop is basically the realization that our world is not flat. The first and the earliest documents of around Earth date back to the 5th century BCE in ancient Greece. So I guess many of you are already familiar with these arguments put forward by the Greeks. So they observed the way boats disappear in the horizon. They also observed the lunar eclipses, where the shadow of the Earth is cast on the moon. So they observed that the shadow of the Earth is always an arc of a circle, whatever the configuration is. So whether the sun is here or there, it's always an arc of a circle. So they did induce that the shape of the Earth must be round. And also the constellations, the way they change depending on where you are on the round surface of the planet. So achievements are locked, at least for most of humanity. There are still some flat earthers today, but let's not care about them for now. But starting from the 5th century BCE, we know that the Earth is round, but it's still the center of the universe. So the next efforts were done still by the Greeks. It's a continuation of that superpower, imagining the world from outside. But the Greeks went a notch further, and they did it in a way more rigorous way. So they used something called mathematics, geometry, and they managed to do miracles with it. Okay, this is one of my all-time heroes of science. His name is Aristarchus of Samos, and he has a book in which, mind you, he measured the distance between the Earth and the Moon, and he measured the distance between the Earth and the Sun. And this looks impossible, this looks incredible. How can you measure? I mean, they didn't have space rockets or anything. They couldn't go to the moon and measure. They didn't have a tape to go all the way to the moon and measure it, but they found a way to do it. So I'm going to ask you to guess how they did it. Okay, let's just try to think of this question here. And I think we have chalk here, so if any one of you that is not a professional astronomer, so that the question is not too easy for you, anyone else, if you can think, let's say I give you an object of a given size. Let's say this circle over here, it's a clock actually, but let's pretend it's the moon. Okay, so this is the moon. And let's say I'm a sort of god or oracle, and I will give you the diameter of this moon, okay? Now, can you tell me what is your distance from the moon, just with this information that you have? So if you can think of a way, it uses middle school geometry, so it's nothing fancy. So you're gonna need some tools, but it's very basic tools. It's like things like a ruler or a protractor, middle school kind of geometry tools. But you can do it. So I give you the diameter of this moon, and without you coming from there all the way here, tell me what is your distance from this moon. Yes?
Do we have like the Pythagorean theorem or geometry of science, law of science? Do we know that yet?
Yeah, the Greeks knew it. So this is our hero who lived, it's 300 BC, so they knew basic geometry, yeah.
So we can imagine that the right angle from the middle of the moon to the edge relative to our view, sine of that angle, distance on the far side, the same as sine of the opposite angle to the distance.
Do you wanna give it a try? Draw it? Maybe we can applaud him to encourage him to come over. You're not a professional astronomer.
I haven't done math in years.
You haven't done math in years. Okay, great.
Here?
Anywhere, here is fine.
There's a moon. There's a right angle. We know this, so we got a little light bulb. And
Yeah.
then we've got a sine of this angle is proportional to that is the same as the sine of that angle proportional to this, right?
Okay,
that
so
right?
how do I, so let's say I know this, right? Yeah, we know this distance. So how, again, so how do I get, so we want to know the distance from you to the moon. So how like, okay.
Go for it.
This is the right diagram, by the way. This is the right diagram. It's almost there, yeah. So there are two ways to do it, depending on which tools you want to use. So let's say you want to use a ruler, okay? So you have a ruler, because I've seen some people here doing things like that. So that's a ruler method. So let's say you have a ruler. All what you do is, let's imagine that the moon is out there. So what I do is I take my hand like this, and I have a ruler here, so it gives me the length of this segment, and then I try to align this ruler with the moon. So the ruler is exactly aligned with the moon, so I am going to have a distance here, and then what I do, I also measure the length of my arm. So in this diagram, it's going to be something like this. Okay, so I'm going to have this, it's known, so let's call it H1, and this is also known, this is the length of my arm, let's call it D1. And then the property that we use, the amazing property, is that this proportion here is the same, the proportion between the, in English it's called the opposite and the adjacent, right? Because I studied this in French. So it's the same as this opposite divided by this adjacent, but also this one divided by this one. So yeah, you don't have to go to the moon, you just need to measure this length and this length, and you have your distance to the moon. So it's H1 divided by P1 equals, let's call it R, the radius of the moon, divided by D, the distance to the moon, and then you can easily derive that D is R times D1 divided by what? By H1, okay? So you can do this math and you can measure your distance to the moon without going to the moon. Yeah?
That's how they do the radius of the moon or the diameter.
Great question. So in my example, I said I'm an oracle, a mysterious deity that gives you the diameter of the moon. I'm going to show you in the next slide how they get that. Our hero, Aristarchus of Samos, answered your question through doing multiple observations. So it's a set of equations through which you can, simplify some of the terms, and you will get the actual answers. Okay? It's a little bit long to explain, so I'm just going to tell you which observations he did. But through these 4 observations, he managed to measure the distances and the sizes of the moon and the sun. So he basically measured the moon itself, which is very similar to what we have done. He measured this angle theta that we were just talking about. He also did observations during the lunar and solar eclipses, which is these 2 diagrams here. And he observed the moon through a specific phase, which is the quarter moon phase. And through these 4 combinations, you do the math, you get a set of equations, a lot of stuff simplifies, and you get your magic numbers. It's worth noting that we are lucky because we live in a universe in which this figure here is possible. So the one, I don't know if you can see the mouse. Yeah, you can see the mouse. So in this figure, the moon is exactly the same apparent diameter of the moon is the same as the sun. And it didn't have to be that way. So you can imagine other solar systems in which this is not the case. So we just got lucky, or the Greeks got lucky because they lived in a universe in which this is possible. Okay? Yeah, so let me stop now in a period that came after the golden age of the Greeks. There was this period that is referred to as the golden age of Islam. I put it between quotes because in French, actually, they call it la civilisation arabo-musulmane. Donc, so there's the French, the Arabic. There's Arabic and Islam in the same, word. But I always put this between quotes because a lot of the contributions to this era of history actually were made by people who were not Muslims and people who were not Arab, of Arabic descent. Although most of the published work was in the Arabic language, and most of the contributors were of the Islamic faith, but some of them were, for example, Jewish, living in south of Spain, the area you see here, or some of them were also non-religious. So there's a famous physician, medical doctor called Al-Razi, Abu Bakr Al-Razi. He's the teacher of another famous physician called Avicenna. Who has heard of Avicenna? Ibn Sina, Avicenna. Yeah, so this is his teacher. He's another legend of the golden age of Islam. He was a deist. Okay, he was not Muslim. So it was an era of flourishing in which a lot of the the natural sciences, but also philosophy, mathematics, medicine, and healthcare had significant advances. In the area of astronomy, the models were mostly based on the Ptolemaic. So Ptolemy is a Greek astronomer. So still in the model of Earth as the center of the universe, but significant works in observing and cataloging the sky. Hundreds of stars that are visible in the night sky still have to this day Arabic or Latinized names since this era. In the Orion constellation, for example, the famous star Betelgeuse comes from Arabic, Yed al-Jawza, or the hand of Orion. Rigel, also another star in the same constellation, in Arabic means foot, and so on and so on. So also lots of advancements in terms of observation tools and methods. Okay, if you see here in the picture on the bottom, on the left, you see some of these measurement devices, very similar to the, if you remember, the protractor that we were about to use to measure the diameter. I was planning to bring you an actual full-fledged instrument called the astrolabe. I guess many of you have heard about the astrolabe, but I didn't manage to bring the full one. I brought just a decorative piece, which is, they claim it's functional. I haven't tried it yet, but it looks like this. Okay, so it's a portable device that allows you to measure elevation of objects relative to the horizon. Okay, so you have to hold it and leave it hang like this, so that because of the weight, the 0 degree here is aligned with the horizon, and then you can make observations to measure things like this. Okay, but it did way more than that. So I have actually some pictures here. So as you can see, you have these lines, they're called abacus. Some people describe it as an analog computer. So basically the way it works is you're gonna use these dials here to point to some points in the sky, or some stars, or the sun for that matter, but without looking at for the sun, you just have to look and make sure that the shadow is a point on your body or on a wall, because you cannot look at the star, at the sun. But yeah, so it's like almost as if you enter some parameters here through these dials, and then you have some other objects that you turn, so that it gives you outputs. And the outputs could be anything from your latitude on planet Earth. It could be the month or the day and the month of the year. And this was developed by Muslims, so it also could tell you prayer times and the direction of the Kaaba, the holy mosque where that Muslims pray towards. But I want to show you a very interesting set of contributions from this era, which are being recognized more and more by historians of science, which have to do with the scientific method. Okay, so I'm going to read to you a small paragraph from a physicist who was called Ibn al-Haytham, Latinized as Al-Hazen. And as we read this, we will see that there are a lot of elements that are reminiscent of the scientific method. So this is not the full-fledged scientific method, the modern one, that took centuries and centuries of elaboration and of philosophy. It's actually a problem that is not even solved today. There is actually in philosophy a problem called the demarcation problem, which is all about what is science. So it's still a very relevant topic, but at least you can see some of the major ideas of the scientific thinking in this quote. So he says, truth is sought for its own sake. It is not the person who studies the books of his predecessors and gives a free rein to his natural disposition to regard them favorably who is the seeker after the truth. Okay? So we know this today as a confirmation bias. So if you read a book and you say, oh, this book is we know that the author is a good guy, we know he says the truth, so it's a confirmation bias that will always drive you to always believe what's in the book. So Ibn al-Haytham says, no, that's not how you should approach these kind of problems, but rather the person who is thinking about them and is filled with doubts. So this is what we call scientific skepticism. It's the faculty of taking distance from whatever you're studying so that you can build as accurate as possible of a view. So a person who studies scientific books with a view to knowing the truth ought to turn himself into a hostile critic of everything that he studies. Okay? If he takes this course, the truth will be revealed to him and the flaws in the writing of his predecessors will stand out clearly. I'm not going to read through everything, but we see a lot of ideas around empiricism, so experimentation. So this is another figure from that era. It's called Jabir ibn Hayyan. He was an alchemist / chemist. Both things were intermingled back then. And we can see a lot of experimentation. Don't believe anything that you hear. I'm only going to include in my book the things that I have experimented with myself, not what I heard other people say, and so on. So the scientific method will be very key in the subsequent explosion of scientific knowledge. Maybe what you've seen here with the Golden Age was the warm-up party, but the actual big party and the fireworks happened in Europe. This is an image of the Copernican model. So this is where so this is called the Copernican revolution, where it was established that the sun is the center of the universe and not the earth. Okay, so it is called the Copernican revolution, but contributions to this idea that the sun is at the center were made before Copernicus and after Copernicus. For example, remember my hero of all times, the Aristarchus of Samos, that measured the distances to the moon and to the sun? That was actually in a heliocentric model. That was the calculation that he did were supposing that the sun is the center of the universe and not the earth. But this said, throughout most of this period before Galileo, it was not very intuitive. So to say that the earth revolves around the sun. Why do you think so? So why is it that if I go to the 12th century or 11th century and go to a market and start telling people that the sun is the center and the earth revolves around the sun, why would they say is wrong, you're wrong, that's not the way it is?
That's not what they've observed.
Yes?
That's not what they personally
Yeah,
observed.
people when they look at the sky, they see that stuff revolve around them. What else?
Because humans are self-centered.
Yeah, it's like a natural bias to think that everything is about us. Yeah. What else? Yes.
The ground is not moving.
The ground is not moving. Exactly. And actually, these arguments I've read it. You can read it in many of the ancient books. So when they are destroying the model of the center at the sun at the center, they say, "Oh, these are just stupid people. How could the earth be moving if we don't feel the movement?" So if I take a bucket of water and I push it, intuitively you feel that the water is going to be all over the place. So how could Earth be moving through space if the Pacific Ocean is not already here, showering us with the tsunamis and all that crazy stuff? Okay, so it will take actually all the way to Isaac Newton, who would answer exactly these questions through fundamental physics, the physics of movement, to really settle the discussion and to put the last nail in the coffin of the geocentric model. But really the empirical evidence that were the strongest empirical evidence were for a model in which the sun is at the center were put forward by Galileo Galilei thanks to the telescope. So it was the turning point was the invention of the telescope, which is a device with which you can see remote things, you can see them closer. What do you think would be the first thing that Galileo would have done after he invented his fancy telescope? What would have been the...
Probably pointed at the sun.
Not to point to the sun and gets blind, yeah. Other than that.
He looked at the moon and he saw mountains.
Yeah, that's the thing. That's the thing. We all think that the first thing that Galileo did with the telescope was to point it to the sky, but
Well, he looked at the ship to battle stocks or something. I don't know.
to what?
He looked at the ship coming from the ocean and to battle in the market. I think that's what he did.
To do what?
To make money.
To make money, yeah. But even more importantly, to look at the enemy's armies that are coming to kill you. So if you had that advantage, then you could, your army can be as big as possible and can be as smart as possible, and they can go from all directions and try to attack you. But if you have a telescope, you can actually beat them very easily because you are way ahead of them. So that was actually the first use of the telescope. It was for military purposes, and Galileo made a lot of money of it. But to his credit, he also pointed it to the moon and to other objects in the sky, and he made revolution after revolution and discovery after discovery that has changed how we perceive our place in the universe. So the picture you see here is Jupiter. It's a pity we're probably not going to be able to see it because Jupiter is out in the sky today, and we could have seen this. And whenever I see Jupiter through the telescope, I feel something because I know that the first person who did that observation was Galileo, and that observation was a huge deal. So the observation is that Galileo had moons. Okay, Galileo had moons. So Jupiter looks like dots, a very bright dot in the sky, but you cannot see the moons. But with the telescope, you can see the moons of Jupiter. And why it's a big deal? Why do you think it's a big deal for people back then in the 16th century?
The Earth's not the only thing with a satellite.
Yeah. So the wisdom, basically in that period, Aristotle was almost a sort of deity. So whatever Aristotle said is the truth. And Aristotle said that everything in the sky revolves around the Earth. So the Earth is the center, and 100% of the stuff in the sky revolves around the Earth. But now Galileo discovers a counter-example. So here is something in the sky that revolves around something else in the sky, not around the Earth. Okay, so he observed these small dots over there. There's three of them, but the fourth one is hiding probably behind Jupiter. There are four called Galilean moons of Jupiter. He observed them, and he noticed that they revolve around Jupiter. So it was a clear counterexample of Aristotle. So Aristotle has been lying to us all this time. So what else did he lie about? Okay. But the most direct evidence was the phases of Venus. So the discovery that Venus has phases just like the moon, and the only way to explain it is that the sun is at the center. This is the drawing of Galileo himself. Okay, achievement unlocked. The sun is at the center of the whole universe, and Earth is just like any of those other so-called wandering planets, which are Jupiter, Saturn, Venus, Mercury, and Mars. And now Earth joins them as one of those other objects that revolve around the sun. Then there is this figure. Who has heard about Giordano Bruno? Yes. So Giordano Bruno was not an astronomer, he was a mystic, and he went further than Copernicus. So Copernicus, in the Copernican model, the sun is at the center of the universe, and everything else in the universe revolves around the sun. But Giordano Bruno went further. He says, yes, the sun is at the center, and Earth and those other wandering planets, Jupiter and Saturn and Mars and Venus and Mercury, they all revolve around the sun. But the other millions of points in the sky, they are other suns. And each of those millions of stars in the sky is a sun by itself, around which there are other Earths, and on this Earth there are probably other Giordano Brunos in these millions of worlds. Okay? So he was not an astronomer. His ideas came more from a spiritual point of view. He used to have these dreams and visions, and he considered that the firmaments or God's firmaments can only be infinite because God is infinite, and that brought him a lot of trouble, as at least you know probably. He got called by the Inquisition, and they asked him to stop saying these heresies, and they ultimately killed him and burned his body. 200 years after Giordano Bruno, scientists, this time astronomers, showed that he was right. Okay, so in the 19th century, it was shown that basically the sun is another star, and I'm going to show you how. Okay, so the technique that was used is called the parallax, and it's very easy to imagine at least the basic principle of how it works. If you take your finger at arm's distance and you keep winking at it, so you close the right eye and then you close the left eye like this, you will notice that your finger shifts places compared to the background, compared to stuff that are far away. Yeah. So according to you, when am I gonna get a bigger shift between the left and right image? Is it when the finger is closer to my eyes, or is it when the finger is further from my eyes? Closer to my eyes. And it's great because I see a lot of people actually doing it. When I give this talk in Morocco, so the point I make is that whenever you are faced with a question to which you can answer by actually doing an experiment, just go ahead and do it. I mean, yeah, you will look like a fool in a room like this, blinking like a crazy person, but that's the idea, is that experimentation, empiricism. Yeah, so some of you may say, what does it have to do with stars? Because after the clouds clear up from Berkeley, and we go, and if we could spend the whole night winking like crazy people at the sky, no star will move, because the stars are very, very far away, contrary to our finger. Unless we had a giant head, we had someone with a head that is so big that the distance between the right eye and the left eye is millions of kilometers. So if we had the giant head, we could actually do something with the stars, and fortunately there is such a head. So again, who can guess? Yes?
When the Earth is 6 months apart in its orbit, right?
Yeah, exactly. Applause? Yeah, that's exactly it. So the Earth revolves around the sun, so you can just guess some stars. You can say maybe these stars are close enough for these effects to appear. And then you take pictures of that same star with 6 months distance. So this is January, February, March, April, May, and then in June you take again a picture of that star, and then you compare the two pictures. So this has been done in the 19th century by a German astronomer called Friedrich Bessel, and I'm going to show you the actual star that he observed. So it's this one. It's called 61 Cygni. It's actually a double star, so these are two stars that are located close to each other. It's a binary system. And if you see very carefully, you will see that all of the stars in the background are fixed, are in their places, but these two stars, the 61 Cygni stars, they slightly shift. Okay? So it's again thanks to the tech people, thanks to the technology of telescopes and optics. It was possible in the beginning of the 19th century to have telescopes that have enough resolution to measure this angle here. So once you measure the angle, you use just, again, like tricks like this one, middle school geometry, and you can measure the distance to the star. Okay? So again, a magic trick in which you can measure distances to objects that are very, very, very far away. Once you measure the distance, what else can you do? Once you measure the distance to stars, you can know what are stars. You can actually answer the question and give credit to Giordano Bruno and show that the other dots in the sky are other suns. How would you do that? So you know your distance to a star. Okay, so those millions of dots in the sky, you know the distance to it. And you want to know what are these things. You want to show that they are suns. And you know the distance. Yeah.
You could compare the brightness with stars closer by.
You can compare what?
The brightness.
The brightness. Yeah. More specifically, so yeah.
Maybe something with the wavelength and.
You don't have to go to wavelength. This is not. It was not known back then. This is the beginning of the 19th century. So you just had light. You could measure indeed brightness and luminosity, but nothing yet in spectrometry.
You can change the, check the difference in brightness
Between?
for the same star. As the planet revolves around.
No, you won't get any difference. It's the same. It's too small. Yes.
The size.
Yeah. The size, yes, but no. Okay. Yes, but no. So you could think of doing something like this, right? So you have the distance, which means you also have, let's say you have this angle, and then you can measure the size, and then if the size is comparable to the size of the sun, then you say these are other suns, right? That makes sense. Except that this angle is 0 for stars. So stars are point light sources, so you cannot you cannot measure this resolution with 19th century telescopes. So you do something very similar, which is also related to what the other gentleman talked about, which is the brightness. So you know your distance to a star, and you know how faint it becomes with distance, so you can know how bright it is intrinsically. Okay, you do that math, and you find out that these stars are the intrinsic luminosity, so the amount of energy that they release is similar to the sun. So they are suns, okay? Yeah. So now we know that through empirical evidence that the millions of dots that we see in the sky are other suns out there, that if we take a spaceship and we go away from the sun and towards the direction of one of the stars, if we look back, we will see that the sun gets smaller and smaller and smaller, and if we look at the star we are heading to, it becomes brighter and brighter and brighter, and when we arrive to that star, it became the sun. And our initial sun, it's just one star among other millions of other stars. Another achievement unlocked. We still have 2 more to go. And the next achievement in this journey was made by an unexpected scientist. So there were a few surveys done on children in the 1960s where they asked children to imagine or to draw a scientist. And it was very striking because most of the children, they drew the image of a man, also with a beard, like an Albert Einstein kind of figure. This is getting better. So nowadays, children, when they're asked the same question, they draw 50-50, men or women. But yeah, our hero here in this station is a woman. She's called Henrietta Leavitt. She was part of a team called the Harvard Computers. The director of the observatory, his name is Edward Pickering, hired a team of women for financial purposes, because they were paid much cheaper, a much lower salary than their male colleagues. Inclusiveness was not a thing back then. This is the beginning of the 20th century. So they were paid very low salary, and they were given tedious and like as if they were computers. So they were human computers. They would do a lot of mathematics. They had to do very meticulous work to analyze photographic plates coming from the observatory and to classify the stars. So one of these Harvard computers would come up with a discovery that will completely revolutionize astronomy since then. So the discovery was, she laid basically the foundations to find an algorithm or a way to find our distance in kilometers or light years or whatever to any stars, no matter how far it is, as long as it's a specific type of stars called Cepheid variables. So those are variable stars in the sense that the luminosity of the star changes across days and weeks and months. This is definitely not the twinkling, when you see the stars twinkle, not that. It's the brightness of the star that changes throughout long periods. If you see in the graph on the top right, so here it's periods of days. So once you have this type of stars that are called Cepheid variables, once you measure the period through which the brightness oscillates, then you can measure your distance to that star. Okay, it's an amazing discovery. It means that you can measure the distance to stars that are way far away, further away than the limits with the parallax, you know, the winking method that you've seen, because that only works for nearby stars. So thanks to this discovery and other discoveries made by women in the first half of the 20th century, these people managed to impose respect for contributions of ladies in astronomy and in science in general. The lady over there to the right, Cecilia Payne, she made other discoveries on what are stars made of, what is the sun made of. The lady at the bottom, Vera Rubin, she made contributions to what we call today dark matter. So when you come up with this very heavyweight discoveries, you impose respects on the community. So 2 years after the death of Henrietta Leavitt, Edwin Hubble, another American astronomer, would use her results or her method to make our next revolution in our place in the universe. So this was the universe back then in 1929. This structure that who has seen this like in real life, not in a picture or a video, but like really, yeah, very a few people, but all of you obviously you've seen it in a very dark sky, definitely not a Berkeley sky. But have you seen, did you raise your hand too? No.
Yeah, I was in a remote place in California and I saw it pretty well.
Awesome. So you remember that structure, you know, with the black thing, the patterns inside the. It's almost like a white cloud. It's not like the clouds that bring us the rain, but it's a weird sort of cloud in the sky. It's very beautiful to see. So this was the universe back then. That's all that existed. This is how it would look like if we had the technology to go and see it from outside. Obviously, this is not a real picture, but it was already established that the sun is one dot in the or one star in the outskirts of this structure that we call the Milky Way. But that was it. That was the whole universe. Everything that you see in the sky, everything that exists is here in this structure. We knew the size of the universe back then. It was 100,000 light years. But then there was a debate about a certain type of fuzzy patches in the sky that were called nebulae, the plural of nebula. So this is the Andromeda Nebula. There was a debate about them. So some astronomers said that they were part of our universe, okay, just normal grouping of stars inside our Milky Way. But some others said, no, these are probably other island universes, you know, other Milky Ways out there. So Edwin Hubble, so there's a famous saying in science that says, big claims require big evidence. So this was a big claim to claim that there are other universes out there other than the Milky Way. And Edwin Hubble will come up with the big evidence. So in an evening of the fall of 1923, as Edwin Hubble was working in a photographic plate of the Andromeda Nebula, he discovered that he had made a mistake in the classification of one of the stars of Andromeda. And on one of the most amazing moments of the history of science, he took the red pen and he crossed the old classification N, Nova, and he wrote the real classification of that star, VAR, variable star. Edwin Hubble discovered one of those special stars through which we can know the distance. He added that exclamation mark. That's not part of the nomenclature. It's not part of protocol. It was just being excited. I would have added many exclamation marks. So now it became possible to measure the distance to Andromeda. And so if it's less, so yeah, what's the logic? If it's less than 100,000, it means Andromeda is in our universe. If it's bigger than 100,000 light years, then we have just discovered a new universe. So he did the calculation just like Henrietta Leavitt had showed him. Again, she was dead, unfortunately. She didn't witness the moment. And it was 2.5 million light years. He did some other calculations, and he realized that not only he discovered a new universe, but the new universe he discovered is actually bigger than our own. It's like 140,000 light years across. So our galaxy is just yet another galaxy in the universe. Today, space telescopes like the old Hubble and the new coming James Webb Space Telescope offer us amazing pictures of these structures, these galaxies. This is a picture of the Andromeda galaxy taken by the Hubble telescope. The Andromeda galaxy has 1 trillion stars in it. 1 trillion, that's 1,000 billion. I'll let you do the count it if you want. Yeah, some of the most amazing. This actually was released the day before yesterday from the James Webb Space Telescope. This is infrared picture from JWST. Yeah, whenever you see in galaxies, you see this fuzzy patch. I'm gonna switch just for you to see it a little bit better. Whenever you see like this big fuzzy patch of whiteness, it just means that there are so many stars there and they're so far away that it just looks like a patch of light. But this is also 1 trillion stars. So it was discovered that these structures are dynamic. This is a collision between two galaxies that takes billions of years to take place. And the following picture I'm going to show you, many of you will recognize it. The one I'm going to show you was taken by the Hubble telescope, but James Webb already released a very similar picture a couple of weeks ago. So the way they take these pictures, the way they took the picture I'm going to show you now is they pointed the Hubble telescope to the most, empty, the most boring area in the night sky. So an area where if you look at it with the naked eye, it's going to be black. You will not see anything. But then they pointed the Hubble telescope to that area. If you want to know how small that area is, you put a grain of sand on your thumb, and you put your thumb at arm's distance from your eye, and you point it to the sky, and the area that is covered by the grain of sand in the sky, this is the area that they photographed. Okay? So the picture could have come up completely black, could have had 1 or 2 galaxies. This is the picture that came out. So I've seen this picture many times. I've seen the new one from James Webb, but every time I look at this picture, I feel something, because every single dot here, every pixel here is a galaxy in its own right. Every small scribble there is trillions of stars out there. So this is what you get with a grain of sand covering a small patch in the sky. So imagine what is out there when you do 360 times 360. There is an estimate of 200,000 million stars in the observable universe. I have no idea to explain this number to you because I don't understand it either. The only way for us to try to understand it is by doing some back of the envelope calculations, as Richard Feynman used to call them. So the number of grains of sand in the world are roughly 10 to the power 19. So you would need 4 folds to come to the number of stars in the observable universe. That means you take, so every grain of sand in this picture is a star, okay? Then you take all the grains of sand in the whole world, and then you multiply it by 10. You get like 10 times as much as grains of sand as there are on the planet Earth, 10 times. Then you multiply again 10 times, and again and again, so 4 times. And then you get the number of stars in the observable universe. And the observable universe is a patch of the universe from which light has had enough time to reach us. The actual universe can go way, way beyond that, and some astrophysicists believe that it may be infinite. So I use the word, and the universe is unfathomably big. It's mind-boggling to when you think about, the size of the universe. I'm gonna finish the talk with a couple of pictures. This is a picture. So we're going back now home. Okay, we're going back to our neighborhood, to the solar system. This is a picture of the planet Saturn. The picture was taken by the spacecraft Cassini. The picture is very beautiful in its own right. It's Saturn backlit by the sun from behind. But if you zoom on the picture, on the lower right corner of the picture, you're going to see a small dot there. If you zoom again, you see actually that it's 2 dots. The blue dot is here, is home, it's planet Earth. And the gray dot is the moon. It's our companion in this big and lonely universe. So astrophysicist Carl Sagan famously wrote a book in the 1990s called The Pale Blue Dot, in which he made a series of reflections about pictures like this one. Some of these pictures he actually commissioned. He tried to convince NASA to take pictures like this because he understood the importance of pictures like this. So the reflections he made were around the fact that, everyone that every single human being that has ever lived has been here on this small pale blue dot. Every religion, every language, every country. We don't see the borders between countries from this perspective. The millions of other living species that we share, this pale blue dot with, and that we are threatening with extinction lately. All of this in one small speck of dust that is revolving around a star among 100 billion stars in the Milky Way, which is a galaxy among trillions of other galaxies in the known universe. So does this picture mean that we're insignificant? I don't think so. It's a matter of debate, but I don't think so. Because the human brain, is the only known object in the universe, as far as we know, that can make this reflection, that can actually think about this. Yeah?
No, I'm just doing that.
Yeah, it's mind-boggling. So when we've seen this picture here, every single one of you had a sort of imprint of this picture in your brain. So you have seen it, you have thought about it, so you have a sort of carbon copy, although it's a smaller quality than the real thing in the universe, but you had a sort of shadow of this image in your mind, and this is something that only humans can do. We can think about how the universe, how big the universe is, and we can ask ourselves these questions. Okay, so there are a lot of still open questions. Maybe we don't know whether these planets have something like life, similar to the life we have here on Earth, whether there are civilizations, consciousness out there in the universe. There are many open questions, and the only way for us to know the answers is to continue the journey. So My last image is this one. It's called the Black Marble. It's actually a series of pictures that were released by NASA in 2017, and they show planet Earth in the night side, or the dark side of planet Earth. And I want you to think of the following. If you had an alien spacecraft that came to visit the Earth 5,000 years ago, back in the time when those ancient monuments we started the talk with, when they were being built, and then that same alien spacecraft left and came back today, what would they think? They would be like, what's happening here? What is this? It's almost as humans are behaving as a sort of organism itself that it has its own, it's doing things to the ecosystem on the planet. It's as if planet Earth is lighting up. Now, the planet itself is lighting up. Obviously, the impact of humans goes way far beyond just lighting up the planet. We are also changing the climate, changing the ecosystem. And this is scaring some people. So some people are worried that, the pace through which science and technology advances have been going through the past centuries, or maybe even decades, is mind-boggling, exponential. So some people are worried that the amount of power that we accumulated, is it proportional to the wisdom that we have today at this point of time in the history of mankind? So these people are worried about things like the risk of nuclear warfare, things like biological leaks, things like autonomous killing robots. So those are robots that are starting to be used now in war, where the drone itself has the ability to decide whether to kill a human being or not. They are being used in Ukraine as we speak. Think of some crazy person or entity or organization that wants to commit suicide, but not just the personal suicide, but also suicide for mankind. So if such a crazy person had their hand on genetic engineering tools that are getting cheaper and cheaper, maybe the journey will not continue. Maybe we'll not find out whether there are other conscious life in the universe. So institutions like the ones where we are here, UCB, Berkeley, Harvard, Princeton, CNRS in Paris, or the Max Planck Institute in Germany, and many, many, many others, will keep pushing the limits of science and technology. But it is also up to us, all of us, as the global community, to also keep pushing the limits of education, of sharing the good word, of sharing these stories of science, and maybe stories of other topics other than science that unite us. Stories that uplift us, and stories that inspire us to treat others with kindness and love and compassion, so that the journey continues. Thank you.